I'm going to do right now is write down a couple of things. One, I have an appointment, previously scheduled appointment for tomorrow at 2 o'clock. So we will not meet tomorrow, but I will have a video up for y'all to watch. So make sure tomorrow, I know you're heartbroken, but tomorrow I will put up a video. I don't know what it's going to be on yet because I got to see how far I get today. Now, no class, but I will put up a video and you are responsible for that material. Second thing, we have covered difference quotient. Well, let me go over here and go to the important stuff. Power, product, quotient,
message coming in on secured channel.
Chain, log, and exponent. That's 80% of your test. No, 70% of your test. All right. Difference quotient, related rates, trig, and rate of change, 30%. So if I give you 10 questions, 7 of them are going to come from here, and 3 or 4 of them are going to come from here. All right, so I just want to give you some kind of perspective. Today we're going to cover rate of change and related rates. Now my plan is to get related rates and rate of change out of the way, maybe give y'all a video on hyperbolic tomorrow. I don't know yet. And then the rest of the week, Wednesday and Thursday, go over nothing but homework questions and the test. That's my plan. Okay, I don't know if that's going to happen or not, but that's my plan. And the worst case scenario is I go over the test Monday and give y'all Tuesday through Friday to take the test while we're going over new material. I'd rather not do that. I'd rather give you the review Thursday and you have the whole weekend to do the test, and then we start material Monday. That's my rather. You okay? So this is what we're looking like. So with that being said, let's get into, I think this is 3.6 and this is 3.11. I think. Let me look, make sure, yeah. Now, I'm not going to make a lot of, I'm going to show you the important stuff in rate of change, 3.6, and related rates. .11. Rate of change, we're talking about f of x, f prime of x, f double prime of x, f triple prime of x. First, second, and third derivative. First derivative is usually what? Acceleration. Or velocity, I'm sorry. Velocity. Your double prime is acceleration. And third is the jerk. And you'll get into that later into physics with motion and the changes in acceleration and velocity is called the jerk. All right, in business, this will give you your increasing and decreasing values. It'll also give you your marginal cost. And the second derivative will give you your inflection points and other things. I'm not going to get into other things, but in other words, the first and second derivative is not only in science and engineering, but it's also in business and economics. So it's very important that you understand the first and second derivative. Where rate of change or related rates, that's a little bit different. The related rates we're going to be talking about as one goes up, the other goes down. And this is another way of thinking, okay? I'll give you an example right quick. Oh, me. Okay, somebody look at that. Now I want you to look at it because I'm going to show you about 4 or 5 different graphics here. And what I'm doing is getting you to think in a different way. Somebody tell me what's increasing and what's decreasing.
The X and the Y.
As X increases, Y decreases. As Y increases, X decreases. That's called related rates. Now, I'm spending a little bit of extra time on the graphics here because you'd be surprised on how many people go through calculus. Some of y'all have had a calculus class, whether it be in high school or whether it be in college, not successful, or whether you're retaking this class again, whatever the case may be. And they go through calculus and they don't have any idea what a related rate is. Here's your picture of a related rate. As one dimension goes one way, the other dimension goes the other. As X decreases, Y increases. As Y decreases, X what? Increases. What's the only way to break this chain? To break the ladder. Did you see that? The only way that you can stop this is to either stop the ladder from moving or break it. Does everybody understand that? You got to think in terms of related rates. Somebody tell me what's changing. Be careful here. I'll give you this much. As X decreases, what increases? Anybody?
To be distance traveled by the boat.
Well, look right here. The angle. What's the angle doing?
It's increasing.
The angle's increasing. Now you could look at it as angle. But X is, as the distance from the boat to the dock decreases, the angle of the rope increases. Again, that's a related what? A related rate. Capiche? And when you get to the rope is equal to 0, the theta is equal to 90 degrees. And look at what the derivative is doing. Okay? So let's look at this. Now this one, are you going to see this again? Oh, hail to the yes. So you might want to write this one down. Are you ready? I'm going to ask you what's changing, and I want you to be very careful, okay? Because your goal on this is to fill up the tank with water, the water being the blue stuff. Your goal is to fill up the tank. That's your goal. I want you to tell me what's changing, but I want you to look at it 2 or 3 times because the goal is to fill up the tank. So that takes one variable out because, you know, that variable is going to be maxed. So which one is changing? All right, I'm going to give you a chance to answer. Somebody tell me.
Would it be the volume?
No, not the volume. We're thinking of dimensions, not area or volume. I want you to, what?
The height of the water.
Okay, you're close. Remember I told you that you want the height is increasing. What else is increasing as the height increases?
The radius. Width.
Okay, I want you to write that down and highlight it because you're going to see this again. All right, I'm going to draw a picture of it. And the reason I'm going to draw a picture of it is I want to show you what the significance is. So if you want to draw this, I would highly suggest that you draw this. And I'm just going to draw, well, I don't have to worry about that. But as you can see from the graphic, you see that each one of these radii as the height of the water goes up, the radius increases. Now, why am I worried about the radius? Because what is the volume of a circle? What is the volume of a circle?
Pi r squared.
R squared. Well, Hubert, why are you drawing? Well, this is called a disk. And a disk is a circle with a thickness about it. Think of a washer, okay, or a disc. Okay, think of a quarter or a dime. All right, let's say this is a dime. This is a nickel. This is a quarter. And this is a 50-cent piece. Okay, the radius on all of them are different. So all I care about is the radius in regards to the height. So what does that mean, Hubert? Well, let's say that they give you, and I think that question that gave you a height of 5 and a length right there of 2. And this is R, and this is height. And the first thing you're going to do is you're going to solve. 5 is to 2. 5 is to 2 as what? H is to what? H is to R. You're going to solve. 5R is equal to 2H. and you automatically solve for R, 2/5 H. Why do you solve for R, Hubert? Because one, it's the thing that's changing, and what's your goal? Your goal is to fill up the what?
The tank.
Your goal is to fill up the tank. So if that tank is 20 meters tall, then you know your height is going to be 20 meters. You know the height. Okay? So that's irrelevant. The R has to be plugged in. Pi R what? Pi R squared. So that R is going to be what? It's going to be substituted in as far as height. Everybody with me? Now, is that going to happen every time with a conical tank? Yes. So the conical tank, you know you've got to get R what? As far as a related rate equal to something. Because the R is changing as you approach your goal of 20 feet or 20 meters or whatever the height of the tank is. Everybody see that? You'd be surprised on how many students don't see it. And like I say, this means a lot right here. If you just look at that for about 2 or 3 seconds and just say, well, the height is being achieved. The height, that's the goal of the tank, to fill up the tank. So R is changing as H increases. That is a related rate. Okay? And of course, you see the lamp post. Is this a standardized test question? Yes. Somebody tell me what happens to your shadow as you walk away from a light.
It gets longer.
It gets longer. So X increases as theta what?
Decreases.
Decreases. That's another related rate. See, when you go back here, well, I didn't mean to do that. Well, I can't move it right now, but when it starts off, that gum, I done got rid of everything now. Whatever. Anyway, how did I move it? Oh well. When the man is right here, the angle of the shadow is like 90 degrees. And you see that the angle is decreasing as the shadow increases. So these are just things that you're going to see in the future as the plane comes forward and it hits directly above the searchlight. It's 0 degrees, and then as theta increases, the distance increases. As the distance decreases, theta decreases. Related rate, theta, with time, of course, but with the distance.
Go what?
What? Say again? Okay. So that's what your related rates are. So what are you going to study with your related rates? Well, these are what you're going to study with your related rates. You're going to study similar triangles. You're going to study your Pythagorean theorem. And you're going to remember your basic trig. Okay? And the one thing I am going to talk to you about is number one, you got to find your function, determine your function. And then once you determine your function, you will need to take the derivative. We'll get to that in just a minute. Okay, so that's where we're heading, and hopefully we'll get a little touch of this and a little touch of this in the next, 45 minutes, and therefore you can start working on those two sections. So let me go to a homework question. Let's pull up one out of 3.6. Okay, write this question down. Wait, the 3.6. Yep, this is what you call cost and marginal cost and average cost. And I'm going to give you everything to do here. This is a test question, so write it down. And I'm going to write it down with you and cover up all the answers. So here, consider the following cost function. Okay, C of X is equal to 0.2X plus 1900. And the domain is between 0 and 5,000. All right, finish writing it. Okay, and they also give you X is equal to A, and A or X is equal to 2,300. I don't know why they have to complicate things. X is equal to 2,300. Okay, now first of all, what the heck is all this? Okay, because some of y'all are not economic people, and some of you are not economists, and some of you have never had a business class before. Well, this is cost. This is your formula for cost, making X units. Okay, that's the function for cost. So if you want to find out how many 10 units is going to cost, you would plug in 10, and that'd be 2 plus 1,900, which would be $1,902. Okay. If you wanted to find out how much it costs to make a 5,000, you would plug and chug. So go ahead and put this in your handy dandy calculator, and you're going to get a graph. Y-intercept is 1,900, and you've got a 2 over 10, which is 1 over 5. So 1, 2, let's see, 1 over 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So you got a very shallow line like this, and you can only go from 0 to what? That means I want somebody to communicate. You can only go from 0 to what?
The 5,000.
5,000.
5,000. Okay, now this is all we're given. All right, now I want you to write down the following two things, and we're going to write them in fluorescent green and fluorescent orange because I'm out of red, and that red marker is pretty much, well, I got some kind of a magenta marker here I can use. Average cost is your function divided by x. Write that down. And your marginal cost is equal to f prime of x. So I want each of you right now to find the average cost, divide the function by x, and find the marginal cost, take the derivative of the function. So do that right now. All of you should be able to do it. If you can't do it, then we'll just consider that failure. Miss Seiler, you got that 5-gallon bucket of coffee ready? Or is that a coffee milkshake? Which one is it?
Is it what? Oh,
Is it a coffee milkshake or is it coffee?
I mean, it's blended, but it's coffee.
You ever meet somebody that drinks a coffee milkshake? They have milk and cream and sugar and then like 1 scoop of coffee in there?
Yeah, no, I don't do that.
Yeah, I'm not a coffee drinker. I have to make myself drink it in the wintertime. I'd much rather have hot chocolate. All right.
You can never go wrong with hot chocolate.
Say again?
You can never go wrong with hot
I
chocolate.
know. I can't. I just, when I drink coffee black, it tastes like hot water. When I put cream and sugar in it, it tastes like hot water with cream and sugar in it. I don't taste the coffee. I don't know why. So I have to make myself drink it in the wintertime. All right, so there's your graph, and I'm going to go ahead and go to the next page. Now, what did I do here? Notice what I did. I made sure I knew what was going on with the problem. I graphed it. I made sure my domain was here, 0 to 5,000. And I know that X is equal to 2,300 units. So they're going to ask me about that 2,300 units somewhere in the question. So now I'm going to go to the next page. And I'm going to write f of x, or c of x, is equal to 0.2x plus 1,900. And I'm going to write average cost is equal to 0.2x plus 1,900 divided by x, which is going to be equal to 0.2 plus 1,900 over x. So there's my equation for my average cost. Now I'm going to do my equation for marginal cost. Point 2 x to the 1 minus 1 plus 0. And I just took the derivative of this, which is c prime of x is equal to 0.2 period. So there's my average cost, and there's my marginal cost. So let's see what the question's going to ask. And there it is. The average cost function is 0.2 plus 1900 over x. The marginal cost is 2.2. Here's where they tell you to plug 2300 on average cost. So let's go to the handy dandy calculator. And let's plug in 0.2 plus parentheses 1900 divided by 2300. And that's 1.03. So it costs you $1.03 to make up to 2,300 units of whatever you make. So if you're making widgets, it's going to cost you $1.03 to make 2,300 widgets. After that, is 0.2 for every one after that. 0.2 is 20 cents. So 20 cents for each one after that, because that's your marginal cost. $1.03 for 2,300. After 2,300, it's $0.2 or 20 cents per item. And that's what they're asking you right there. Now, I just went over a good test question. It's really not that difficult. We'll do another one here in just a second. They give you the function, they give you the domain, and they give you something to plug and chug.
You have
So
a
that's
quick
what they're
question.
going to ask. Go ahead.
Where'd you get that 2 from again? Not for the.
What's the derivative of 0.2x? Huh?
No. Oh, it's 0.2. Okay.
Yeah, 0.2. That's all. That's a 0.2, and that's a point. Let me blow it up a little bit. I can't.
My bad. I thought that just
Can I
said
blow
2.
it up? No. Yeah, it's 0.2. You just can't see it. All right, let me find another question. I went through the homework and picked out a couple of questions that I would probably put on the test. All right, try this one. Remember, you need to draw what you got first. I want you to get what's given. What do you know about what's given? So I want you to tell me everything you know about what's given before we even start the question. Because I don't want you getting tied up with, well, how do you do this? And I want you to tell me what you know about the problem before we even get started. If you have to sketch a graph, if you have to graph it on your graphing calculator, however you need to do it, I want you to tell me what you know about the problem before we even start on it.
They give you the equation for the problem.
Yep, they give you the equation. S of t is equal to negative 16t squared. Well, that's a quadratic. First thing I would do is go to the calculator. Plus 400. The 400 is worthless because the 400 is basically telling you that's your y-intercept in the formulas. That's why the 400 feet above the ground, that's good, but they don't need to tell you that. Determine the velocity, blah, 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 when it reaches the ground. So we got to find out when that ball or whatever this is reaches the ground. So we got to graph it. So we're going to graph it, and it's going to look like this. We know this is 400, and we throw it. This is time, And we know it hits the ground right here. So we got to find that point before we even start the problem. So we go to our handy dandy calculator. This is what's given. And this is given also. You just got to find it. So take your handy dandy calculator and go y is equal to negative 16 x squared plus 400. And graph it. And I don't really care. I'm going to do a zoom quadrant 1 because it's only going to be in the first quadrant. Because you're throwing a ball, you can't throw the ball backwards. I mean, you can throw the ball backwards, but it's not backwards from, just forget it. See? So I'm going to do zoom O for fit. There we go. And there's the y-axis, and there's our point we need right there. So I'm going to call it second trace 0, which means your x-intercepts. And left side looks like 5. But I don't want to, I want to make sure. What'd y'all get? 5, Hubert. That's good. So at 5 seconds, the ball hits the ground. Well, on this thing, S prime of t would equal your velocity and your S double prime of t would be your acceleration. So derivative, that'd be 2 times 16 negative 32t and negative 32. Now, what's this point? 5 comma what? 0. So at 5 seconds, right here, that's going to be 35 times, or 35 times 32. What is that, 160? So that ball, when it hits the ground, is traveling at 160, and I want to say either meters per second or feet per second, whatever they put this in. And then the acceleration, there is no variable to plug into. So therefore, the answer, no matter what, is negative 32. Sorry. So in this problem, the first thing you have to do is you have to find the equation that you're working with. So I'm going to put a red mark around that. Where are you? What equation are you working with? Okay, that's number 1. Now, number 2 is find out everything you can that's given. Why did I draw this graph? Because I needed this right here. I needed to know when that ball hit the ground. And the graph told me that. And once I found that x, all I had to do was plug it in to the first derivative I can't plug it into the second derivative, so the answer is just negative 32. So there's my two answers. Now, I can guarantee you you're going to see this on the test because I will give you a motion problem because those of you taking physics, that's what you're headed toward. Okay? And there's the first derivative and there's the second derivative. Good? And 160 and negative 32. Question, gripe, complaint. All right, let's jump over to 3.11. And 3.11, that's where we're going to be working with just basic formulas, similar equations, taking the first derivative, that kind of stuff. Well, if my computer will, work with me. Assignments 3.11. And I want to pick one that I would pick for a test. So let's see. All right, let's try that one. Let y'all write it down. It says the sides of a square increase in length at a rate of 4 meters per second. The sides of a square changing when, the sides of a square increase in length at a rate, increase at length at a rate of 4 meters per second. So at that point, that's technically dA dt. I'm writing all this down. I'll show you in just a second. A, at what rate is the area of the square changing? Area of the square changing when sides are 15 meters long. And then B says, at what rate, blah, 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 quote, quotation marks, when the sides are 25 meters long. Okay, there's what we got. Excuse me. Now we'll call this DS, DT. Sides, not the area. The sides of the square. I messed that up. Now, I want you to get used to writing this because this means the sides of the squares are changing with time. The sides of the squares, DS, the sides of the squares, the sides of the shapes are changing with what? Time. You're going from a 15 meter by 15 meter square to a what? 25 meters by 25 meters squared in a period of a few seconds because it's changing 4 meters per second. So I'm just going to remind you, I don't have a square growing, but what I am going to show you, if I can remember, the ladder. Okay, this is a triangle, but the whole point is I'm starting with 4 meters and it's gradually getting up to what? It's gradually getting up from 15 meters to what? 25 meters. So it's kind of growing, kind of like this is growing or X is growing when Y is decreasing. See? Okay, so think of a box sitting here, and in a few seconds, it opens up to a bigger box. Like that. That's what you got to think about. So the rate of growth on the sides, the difference in the sides in regards to time is 4 meters per second. Okay, well, that's nice, Hubert. We understand. What do you do first? Well, the first thing you got to do is you got to get an equation. What are we talking about in this question?
It's the area.
So somebody give me the area of a square.
Be like x times x.
Well, S squared, yes. So I'm going to take my handy dandy and I'm going to write down A is equal to S squared. Now I want you to take the derivative of this function. This is going to be called d big A over dt is equal to 2s, then s ds over dt. Okay, just bear with me. So that's going to be, this is the way, the hold your pinky up way to write it. D big A over D little t. The difference in area, because this is area, the difference in area is changing in regards to what? The difference in what?
The time.
Time. Equals 2s, and then I have to multiply by the growth rate, ds dt. That will have to be multiplied by anything you do because that's the growth rate. Okay, so that's going to have to be multiplied right here. It's going to be in there. So that's ds dt. So with the first one, it's going to be 2 times 15. And what is the derivative, or what is this? 4? And that's going to be 30 times 4, which is what? 120 meters squared per second. So that area is being affected in the 15 meter square at 120 meters squared per second. Okay, so 15 meters is right here. So when as it got up from 4 to 5 to 6 to 7 to 8 to 9 to 10, 11, 12, 13, 14, 15, up until that point, it was growing at 120 meters squared per second. So what is the growth rate in area of this one? Well, of course, A is equal to S squared, B. A is equal to S squared. Therefore, dA over dt is equal to 2S ds dt. And that's going to be 2 times 25 times 4. And that's going to come out to, let's see, 25 times 4 is what? 100. And 100 times 2 is what? 200? 200 meters squared per second. So as you can tell, the first square up to 15 by 14 by 14, it's growing at a rate of 120 meters squared per second. But by the time you get up to, what was it, 25, then it's grown from 120 to 200 meters squared per second. And that's how you do that type of question. So write an equation. What was our equation? 2S. They want something. They want A is equal to 2S or something. I don't know what they want. A is equal. Okay, they want the one you start off with. I'm sorry. There we go. 2S ds. And the first one is 120 meters squared per second. And the second one is 200 meters squared per second. That's a good question. And it's not that drawn out. I did throw a couple of steps in there because, you know, it needs to be done carefully. All right, let's try another. Let's see. We just did that one. Let's try that one. The area of a circle. What's the area of a circle? Somebody tell me quick.
Pi r squared.
Pi r squared. So you know right off that you're going to be taking the derivative of pi r squared. So I would write down A is equal to pi r squared, and then I'd write down the problem. The area is changing. That would be dA dt of equals 4 centimeters squared per second. So write everything out. I'll write everything while y'all are writing. The area of a circle increases at a rate of 4 centimeters squared per second. 4 centimeters squared per second. Therefore, dA over dt, meaning that the area is changing in respect to time, and that's going to be equal to, excuse me, 4 centimeters squared per second. dA dt is equal to 4 centimeters squared per second. And A says, how fast is the radius changing when the radius is 5 centimeters? A, how fast is radius changing when the radius, when r is equal to 5? And B, how fast is the radius changing when the circumference? How fast is the radius changing when the circumference is equal to 1 centimeter? All right, take a minute and work on it. Remember, you're working with pi r squared, the area of a circle.
Hubert, quick question.
Yes.
Would it help if we changed, like, finding the second part, instead of finding that the circumference is 1 centimeter, we say that the radius is 0.5 centimeters?
You could do that. I'm going to
Okay.
do it with the circumference, though. But yes, you could. This is what I've got written down. Well, that's all I've got written down right there. So A is equal to pi r squared. A is equal to pi r squared. So if I took the derivative of this, that would be dA over dt. Okay, we got something to plug in for that later, but that would be dA over dt. So dA
Priority 1 message
over
coming
dt
in on secured channel.
is equal to, well, that's going to come out front. That's going to be 2 pi r. And then dt, I'm sorry, dr, the radius is changing, over dt. Now, the reason I added these is because you haven't been dealing with something changing, okay? You haven't been dealing with that. This is the first section where something is changing, okay? You're given the area increases, so the area is changing, dA over dt. And here, how fast is the radius changing? So the radius is going to be multiplied by the changing rate right here. Okay, so it's going to come out right. It's going to come out neat. So you just have to remember that you can't use A prime. You have to call dA over dt. And here you multiply by the dr, the changing of the radii in regards to time. And basically, I've already done everything. All I got to do now is plug and chug. What do you mean, Hubert? Well, you got R. That goes right there. And then what is this guy? dA over dt, he goes right here. So that should be 4 is equal to 2 pi times 5. And then multiply that by the changing of r over the changing of time. You could actually do this in steps. You could actually divide by 2, you get 2, and then divide by 5. Or you could take 4 times 5, that's 20. And divide this whole thing by 20 on both sides. That will be 1/10. I'm thinking out loud. So that would be 0.1 times pi is equal to dr over dt. So go ahead and solve that. And divide by 2. And that's going to be 2 is equal to pi. So 2/5 is equal to pi. Divide by pi. Let's see, divide by pi over 1, multiply by 1 over pi. So 2 over 5 pi. 2 over 5 pi is equal to the rate of change the difference, the change in the radius over time is 2 over 5 pi. All right, now let's do the same thing here. Now this one is going to be a little bit more complicated because you're dealing with circumference. So circumference is equal to 2 pi r. Now you could solve r is equal to c. Yeah, you could do that. R is equal to c over 2 pi. You could do that. And we know that a is equal to pi r squared. So we can actually take this r and plug it in right there. And that would give you, plug in pi r squared, that'd be pi times, I'm thinking out loud, c over 2 pi quantity squared. And that would be c squared over 4 pi. 4 pi squared. I'm thinking out loud. So that's going to be pi times c squared over 4 pi squared. And that'll take one of your squares out and leave pi. So basically, you're going to get, yeah, you're going to get c squared over 4 pi. C squared over 4 pi. And that's going to be your r. R is equal to c squared over 4 pi. And that's going to be Yeah. Area, I'm sorry, not, that's area. So I'm going to start on the next page. The area for my changing circumference is equal to c squared over 4 pi. And I'm going to take the derivative of that. So d of a over d of t, meaning the area is changing in regards to time, is equal to 1 over 4 pi, pull that out, times c over 2, c squared, and that's going to be the difference in area as regards to time is equal to 1 over 4 pi times 2c times, it's going to be, let's see, if I take the derivative of that, that's going to be dc dt. The change in circumference over the change in time. And I think that's going to be 2c. I think our c is equal to 1. I think given c is equal to 1, we're going to put that in right here. And that's going to be the difference in the area in regards to time of 1 over 4 pi. And I'm going to just say times 2 because 2 times 1 is 2. And then the change in dc over dt, dc over dt, what is that? That's going to be equal to, and we need to finish this one tomorrow. We're running out of time. We'll finish it tomorrow. Or, well, I will finish it on video tomorrow. Okay, let's finish it tomorrow. I'll just redo it. And let me get the roll. I'm glad y'all getting to see a little bit of what you're going to see next semester. That's a good thing.